All right, I'm going to start talking right away because I'm told that you need to start talking right away so that everything is picked up. We're going to talk today about the equilibrium constant. In the last lecture, we talked about equilibrium, and we looked at a situation where we had the conversion of dinitrogen tetraoxide to nitrogen dioxide. And we saw a little graph where we had the concentration of nitrogen dioxide there, and we had the concentration of NO2O4 there. And we said that both concentrations got to a point where, as time progressed, they remained constant. Time, concentration. This period, where the amount of the reactant and the amount of product is unchanged, notice at equilibrium on that graph, the amount of product and reactant are constant and doesn't change. Therefore, we can describe it using a ratio. Because the amount of product and reactant are constant, we can use it describing a ratio. We like to use the ratio of the product present at equilibrium to the ratio of the reactant present at equilibrium. Now, we just can't write the product and the quantity of product at random. We just can't write the quantity of reactant at random. We have to do it in a very specific format. That format incorporates the coefficients in the equations. What do I mean by the coefficients? Well, if we look up at our model equation that we dropped off with last time, where we have nitrogen tetraoxide going to 2 moles of nitrogen dioxide, and I just made that messier trying to highlight the fact that there's a 2 there. Our ratio has to incorporate the fact that there are more moles on one side than the other. So we write the ratio like this, where we take the concentration of the product and we raise it to its coefficient's power. Since we have 2 moles of nitrogen dioxide there, and the ratio will wind up squaring it. And we divide it by the concentration of our reactant. Since the coefficient of our dinitrogen tetraoxide is 1, it's only to the 1 power. So the equilibrium constant is equal to the nitrogen dioxide squared divided by dinitrogen tetraoxide. This ratio of product to reactant is referred to as the equilibrium constant. The ratio of product to reactant is the equilibrium constant. I know that's all messy. Don't worry about it. We're going to go on to the next slide where it's all typed up nice and neat. All right, here's the next slide. For the equilibrium constant for a reversible reaction multiplies the concentrations of the products together and divides by the concentrations of the reactants. It raises the concentration in the molarity of each species to a power that is equal to the coefficient of the balanced chemical equation. For example, we have the world's most generic chemical equation of A moles of A reacting with B moles of B to yield C moles of C and D moles of D. So our equilibrium constant is the concentration of C to the C power divided by the concentration of D to the D power. Products divided by reactants are reactants the concentration of A to the A power, the concentration of B to the B power. And that's your equilibrium constant. Let's take a look at a couple more examples. It's not worth it. All right, let's write the equilibrium constant for this expression right here. I'm going to take my products, concentration of carbon dioxide squared, because I have a 2 there, divide it by the concentration of my reactants. So I'm going to take my concentration of carbon monoxide, and because it has a 2 in front, I'm going to square it, and then I'm going to multiply it by the concentration of oxygen, and it's to the first power since it only has a 1 there. And that would be the equilibrium constant for the reaction. The equilibrium constant is always represented by the capital letter K. Most of the time you'll see one of two little things down here. You'll either see a EQ for equilibrium, or upon occasion you'll often see capital K, lowercase c, meaning that's the equilibrium constant in terms of concentration, where C stands for concentration. I think I've got another. Choose the equilibrium constant for the reaction shown. Wow, this one looks really familiar. We just substituted carbon dioxide for, we just substituted sulfur dioxide for carbon monoxide. But go ahead and write that equilibrium constant. Okay. Pause me and choose your answer. Did you pause me? I told you to pause me. Pause me. Try to figure out the answer on your own. Come on, pause me. I'm not going to talk until you pause me. Well, even if you didn't pause me, I'm hoping you've now gotten so tired of me passive-aggressively telling you to pause the presentation while you figure out the answer on your own that you've figured out the answer on your own. So we're going to write our products. To their power, divided by the concentration of our reactants, raised to their power. And that would give us that one right there. Chemistry's easy, life is hard. Let's keep moving. What we're going to want to do is we're going to play a little bit with the math on this. The math on equilibrium constants actually can be some of the worst that you'll face in undergraduate chemistry. Outside of PChem, that is. Therefore, we're not going to go on too big a deep dive on this, but let's do realize that there are actually numbers attached to that equilibrium constant. Let's take a look real quickly and familiarize ourselves with a pretty common reaction when it comes to talking about equilibrium. And that's the reaction of hydrogen with iodine to form 2 moles of hydrogen iodide. The equilibrium constant for that is going to be the products over the reactants. So we've got hydrogen iodide squared divided by the concentration of hydrogen divided by the concentration of iodine. One of the many fascinating things about equilibrium is that no matter what amounts you start with in terms of reactant and product, the ratio will always wind up being the same as long as the temperature is the same. For example, as long as you hold the temperature constant, then the ratio of hydrogen iodide to hydrogen iodine at the temperature at which this experiment was conducted will always be 54. Now, the concentrations that make up the ratio may not be the same. For example, you can start with one amount and wind up with these quantities at equilibrium, or you might wind up with these quantities at equilibrium if you start with different starting amounts. However, look at what happens when you calculate the ratio. It's equal to 54, equal to 54. Even when we start with the third amount, it's equal to 54. That's why it's referred to as an equilibrium constant. In different experiments, you might wind up having different concentrations that make up the ratio, but the ratio itself is constant. The value of that ratio depends only on the temperature. That's why we call it a constant, because it's constant. So at equilibrium, the ratio of products to reactants is always constant. Let's have you actually calculate the value of an equilibrium constant. We've got my favorite reaction here, and I want you to tell me what the value of the equilibrium constant is at 100 degrees Celsius if the equilibrium mixture contains a concentration of 45 molar dinitrogen tetroxide and 0.31 molar mononitrogen dioxide. And I shouldn't have used mono, there should just be nitrogen dioxide. Step 1, set up your equilibrium constant symbolically. So I know that my equilibrium constant is going to be the concentration of my products divided by the concentrations of my reactants. Now that I've set it up symbolically, I plug in my numbers. So you wind up with an equilibrium constant of 0.21. Chemistry is easy, life is hard, yes? Let's take a look at the next one. You try this one real quickly, especially given how similar this one is to other ones. Take a stab at this. Pause me if you need to. Did you pause me? I hope you paused me and tried working this out on your own. Let's do it again. First thing we're going to do is we're going to set up our equilibrium constant. then plug in your values, right? Your equilibrium constant is always your products over reactants. They told us our equilibrium concentration of hydrogen iodide is 3.5. Hydrogen 1.2, and iodine 1.2 as well. Plug that into our calculator and we get 0.85. Quick question, Dr. Kelly. Dr. Kelly, wait a second. We just looked at a graph where all the results for this reaction were 54. How are we suddenly getting 0.82? Remember I said the equilibrium constant is a function of temperature. Well, that first graph, we were looking at something, that first table of data, we were looking at a different temperature than 443 degrees Celsius, right? We pretty extremely changed the temperature. And when you change the temperature, you do change the value of the equilibrium constant. Let's interpret the equilibrium constant. But before we interpret the equilibrium constant, let's talk about the superhero that probably needed an interpreter, Black Widow. Because originally in the comic book she was from Russia. They kind of glossed over that fact in the movies, or didn't bother to mention it. But why don't you write down Black Widow? Once you've written down Black Widow, let's go back to interpreting the equilibrium constant. The values of the equilibrium constant can be very large or very small. One has more product or one has more reactant. Let's take a look here. Remember that the equilibrium constant is the ratio of products over reactants. When the equilibrium constant is greater than 1, that means that the top number of your fraction is larger than the bottom number of the fraction, right? For example, if you've got 4 divided by 2, you have 2, which is greater than 1. And if you have 4, a big number on top, and a small number on the bottom, that means you have more product than you have reactant. So whenever your equilibrium constant is much, much greater than 1, you will have more product at equilibrium than you will have reactant. The opposite is also true. Let me erase a little bit here. And by opposite, I mean if our equilibrium constant is much less than 1, that means the bottom number of our fraction, representing our reactants, has to be larger than the top number. For example, 2 to 4, right? More reactants than products is 1/2, and 1/2, of course, is less than 1. So whenever you have a value for your equilibrium constant that is much, much less than 1, you have to have more reactant than product. at equilibrium. Alrighty, let's continue on. Here's a quick real-world example. For the reaction of sulfur dioxide with oxygen to form sulfur trioxide, the equilibrium constant at room temperature is 3.4 times 10 to the second, or 340, and 340 is much, much greater than 1, meaning that at equilibrium, you're going to have more products than you do reactants. This is one of those summary slides that you may wish to pause me and write down. Let's take. The opposite's also true. For example, the reaction of nitrogen oxide to form nitrogen monoxide. The equilibrium constant at room temperature for that is 2 times 10 to the negative 9th. That is a whole lot less than 1. So at equilibrium, you'd have a lot more reactants than you would products. Chemistry is easy, life is hard, yes? Just over reactants. Again, another summary slide, just to make sure the horse is thoroughly dead. Actually, I'm going to stop here. Alright, we can also do some mild algebra with equilibrium constants. For the reaction of carbon dioxide and hydrogen, the equilibrium concentrations are 0.25 molar for carbon dioxide, 0.8 molar for hydrogen gas, and 0.5 molar for water. What is the equilibrium concentration for carbon dioxide? I like to organize my data. This is just maybe my own little bugaboo, but I like to write the concentrations underneath my chemical reaction just to help me organize things and make sure that I don't make a mistake later on. They didn't give me that, so I'm going to make that X and 0.50. So those are my equilibrium concentrations. So once I have those organized, next thing I'm going to do is write my equilibrium constant. Products over reactants. So I've got the concentration of carbon monoxide times the concentration of water over the concentration of carbon dioxide times the concentration of hydrogen gas is equal to 0.11. Now I'm going to substitute in the numbers they gave me. Whoops. And I made a mistake already, didn't I? Know what happened? I've got my laptop open at the moment, and a notification icon streaked across my stream, and it distracted me. I wasn't paying attention in class! I'm sorry. I hope you guys are paying better attention than I am. Let's see. I'm not sure what that says if I bore myself. Alright, we've got X. We've got our concentration of carbon monoxide that we're wanting to solve for. We've got our concentration of water. We've got our concentration of carbon dioxide. We've got our concentration of hydrogen. Now it's just a little matter of doing some algebra to solve for X. And let me expand upon the algebra a little bit, because I know people like it when I do algebra in detail. So I'm going to scrunch this up here so I can do my algebra in a little bit more detail. I've got 0.11 equals x times 0.50 divided by 0.25 divided by 0.80. I have to get x by itself, so what am I going to do? Well, I'm dividing by 0.25, so I need to multiply it by it. I'm dividing by 0.8, so I need to multiply by it, so it cancels. I'm multiplying by 0.5, so I need to divide by it, so it cancels. And what I do for one side, I have to do for the other. Whoops, stop that. Come on. Not you, my tablet. So now I punch into my calculator. And I get x to be equal to 0.25 times 0.8 divided by 0.5. One thing I should, and there's my answer. One thing I haven't really addressed, you'll notice that I had m's and m's disappeared and my units seem to be dropping in and out, kind of like pennies from heaven or something. The reason for that is by tradition, the equilibrium constant has no units. Whenever you have an equilibrium constant, it's never 0. In this case, it's not 0.11 moles or anything, molar or anything. It's just 0.11. It's just a number. No units are given. Now, it is always calculated with concentrations in molarity. So it's always calculated with concentrations in molarity. So the numbers that go into it have units of molarity. The numbers that come out of it will also have units of molarity, but the Kc itself doesn't have any units. That's the reason I had m's there, and then that disappeared, and then the big m's dropped back in because it's for molarity. Why don't you write down Falcon? Everybody write down Falcon. Everybody write down Falcon. For each of the two examples shown here, indicate whether the equilibrium mixture contains more products or reactants. Well, to answer this question, you don't even really need these reactions. What you need, right, we don't even need to look at this part, this reaction part here, right? To answer this question, all we really need are these numbers over here. For our first reaction, our K of 10 to the 95th, well, that's a lot greater than 1, which means that our ratio of products over reactants is heavily favored to the products. Down here, we have 1.8 times 10 to the negative 7th. Well, 10 to the negative 7th is much less than 1. So the bottom number of our fraction would have to be larger, meaning that we have to have a lot more reactants at equilibrium if our equilibrium constant is less than 1. Chemistry's easy, life is hard. All right, here's a math one again. Why don't you pause me and try to figure this one out on your own? All right, I know you paused me. I know you did, because you know if you didn't pause me, I will just ramble incoherently until you did pause me. So let's set this up. First thing, set up that equilibrium constant. products over reactants so we have now we plug in our concentrations. It says the concentrations at equilibrium for this and for that are both 0.1. So we've got 0.1 times 0.1 over our concentration of our phosphorus pentachloride that we're wanting to solve for. And that is equal to, that's a 0.1, by the way. My handwriting is really, really sloppy. Is equal to 4.2 times 10 to the negative second. We have our variable on the bottom, so we have to bring it out to the other side. So we've got 0.1 times 0.1 now equals PCl 5 times 4.2 times 10 to the negative second. I've got to get my variable by itself, so now I'm going to divide both sides by 4.2 times 10 to the negative second. And that gives me 0.1 times 0.1 divided by 4.2 second EE negative 2. That gives me 0.238 or 0.24 rather as my final constant molar, of course, as my final concentration of my pentachloride. Wow, my handwriting got sloppy there. And there's my final answer to that one. That's all I have for this segment of the lecture. Why don't you write down Thor and meet me on the next lecture. Thor.